So as I'm sure most of you are aware, our usual format is a single talk by one speaker, which usually lasts whatever it is, 40, 50 minutes or something, and then questions. But in the interest of doing something a little bit different, we've got an experimental kind of new format for tonight, where we have 4 shorter talks by early career researchers. They're all based in the Grant Institute, and we've got 3 PhD students and 1 postdoc. So we'll have a selection of topics. We'll take questions after each of the talks, just if anybody has any questions about stuff. Okay, so the first speaker is Rhi, and you may have noticed if you saw the advert posted that's been around the school, that sort of glowing volcano thing was inspired by, by your topic. So good go, thank you.
Hi, everyone. Thanks for coming to my talk. So I'm a final year PhD student, and I'm working on the deep study of volcanic domes on Venus. So Venus is a sister planet as Earth, given they are similar in composition and density and mass, but different from Earth. Venus is a volcanic planet, so that has a really high surface temperature and pressure, something 100 times higher than that of Earth. And also, so like I said, the lava flow on Venus could be hundreds or thousands of kilometers because of the really dense atmosphere CO2 that can suppress radioactive and convective cooling. And so in this study, so what I'm looking for is how do you just generate this hundreds of thousands of kilometers of lava flow, and their basaltic composition, but they could be really viscous, that might indicate some unusual process happening on Venus. That's what I'm going to tell you today. And before I officially jump to my talk, I would like to draw your attention on the pancake on the left-hand side figure. I assume everybody here loves to eat pancake every day. That is testing, and I have a flat top surface and a perpendicular edge. So in this study, so I have lots of layers accumulated on top of each other. And in this study, what I'm looking for is the pancake-shaped volcanic domes, as we can see on the right-hand side figure. So the figure on the right, those are the real Magellan radar images from NASA's emissions on 1990s. And the scale bar here is really huge. And we can see the diameter of those domes could be something 40 kilometers with a height something 1 kilometer, which is the size of Edinburgh. So they show us a strange structure like a pancake. Therefore, we call this pancake dome. And so here's the definition. So the pancake dome we call a steep-sided dome is a volcanic edifice with a characteristic high-angle margins and relatively horizontal upper surface. And so people have debate about the formation mechanism. Some people say there could be this pancake dome can represent volumetrically real remains of viscosity rich and acidic lava eruption. Other people might believe they come from a really crystal-rich basalt. So in this study, what I'm going to do is use thermodynamic modeling to test which mechanism is correct. So the understanding of the acidic-rich magma or dome formation on Venus is conducive to the understanding of large-scale process on Earth or Venus-like planets that lack plate tectonic. So here's an example for a traditional dome from Newberry Obsidian in Oregon, USA. And so this is a steep-sided dome. The figure on the right here, or left there, top edge, they just show us a steep-sided edge with a height something 40 meters. And the whole topography is a topography of the dome with a diameter something 2.5 kilometers. And those domes, they are made of the rhyolite. That's really silica-rich obsidian lava flow, but they are crystal poor, but they can represent some really viscous lava, and because of the high viscosity. In this study, what I'm looking for is how to use generate steep-sided domes. I try to use the viscosity to constrain the lava viscosity to constrain the formation mechanism. The lava bulk viscosity here that equals to the purely liquid viscosity, which is this function. Like I said, that can depend on the magma composition, such as silica or magnesium oxide, or the water content, and also the crystallinity. In the first part of the talk, I would like to focus on how the magma composition influences the liquid viscosity. For the second part of the talk, I would like to talk about how crystallinity or the effect of water or degassing influence on the magma bulk viscosity. And so the method I'm using here is a thermodynamic modeling software called rhyolite-MELTS. For those who are not familiar with MELTS, MELTS is a software package designed to facilitate the phase equilibrium in magmatic system over a wide range of temperature from 500 to 2000 degrees C and pressure from 0 to 2 gigapascal. And in this study, what I'm trying to perform rhyolite-MELTS modeling of fractional crystallization or partial melting for 2 Venusian compositions, which are listed there, from Russian cylinder on 1980s and Venusian 13 and Venusian 14 at different pressure, temperature, water content, oxygen, fuel gases to probe the magmatic process. For those who are not familiar with, like say, geological terminology, fractional acquisition means as your magma gradually erupt from the deeper to the surface. So you gradually decrease the temperature. Oops. As you gradually transport the magma up, you gradually decrease temperature. At each temperature step, you have minerals precipitated. And the fractional acquisition means the minerals precipitated at a high temperature has been removed from the system. So that's not being accumulated. So on the other hand, like say, in contrast, equilibrium acquisition means as you gradually decrease temperature, all the minerals has been kept in the system, in a closed system without removing them. And so the bulk compositions, mineral 13 and mineral 14, they are both basalt. Mineral 13 is a alkaline-rich basalt, and the mineral 14 is a silica-rich basalt. And those proofs, they are from the Russian emissions. And here's the real, like say, the lander radar image look like. We're lucky because both mineral 13 and mineral 14, they both landed in the pancake dome prone regions. Hopefully, they are representative of the surface composition of those domes. And so here's the real result on the real MELTS modeling I have done. So here's the typical TIS diagram, which is y-axis is the potassium plus sodium content of the liquid, versus the axis is the silica content of the liquid. The color bar here denotes the temperature. And the mineral 13 starting composition, liquid temperature is somewhere there. Mineral 14 composition is somewhere there. So remember, as the magma gradually erupts, it gradually decreases temperature. Mineral 13 evolves towards a more potassium sodium rich composition. And mineral 14 evolves towards a more silica-rich composition. And the increased pressure for both composition gradually decrease the maximum silica content. The novelty of this study is there's a huge uncertainties for the lander, like say, there's uncertainty of error bar for each composition. I use Monte Carlo simulation to generate hundreds, thousands of compositions within the uncertainty of error bar. So therefore, I run hundreds of models within the uncertainty of the bar composition that show us the gray shaded region for mineral 13 and blue shaded region for mineral 14. So we can see this uncertainty trigger a really large variation for the liquid composition. So the figure on the left again is the TS liquid, like say, potassium plus sodium liquid composition versus silica content of the liquid composition. And here is a fractional acquisition of mineral 13 at two pressure 0.01 and 1 gigapascal. On top of this, I calculated the liquid viscosity, which is the figure on the right. The y-axis of the diagram here is the liquid viscosity, is the viscosity versus the axis temperature. And the red marker, triangle marker here represents the composition of mineral 13 at 0.01 gigapascal. That is corresponding to this line. And the green triangles here represents the mineral 13 at 1 gigapascal. That is corresponding to this line. So remember, there's a huge variation for the uncertainties caused by the bar composition reported from the Russian lander. But the good thing is that although there's large uncertainty for the liquid composition, that only resulting in a modest small variation for the liquid viscosity, which is good. So on top of this, I compare the liquid viscosity with previously published physical model. So there's a physical model from Fang et al. 2019. What this suggests, in order to generate gigantic dome on Venus, you need this critical viscosity temperature relation. Or some other studies suggest you need this the orange bar viscosity range there. You need to generate high viscosity for the dome formation. You can see our liquid only viscosity is too low to compare with other published physical model. That means we need to think about other mechanisms. So the first thing I think about is involving the crystallinity. The diagram here is also the viscosity y-axis versus the temperature, which is the x-axis. The red solid line here represents the liquid only viscosity for mineral 13 composition for equilibrium acquisition. By definition, all the minerals has been kept in the system at 0.01 gigapascal. And so the red dashed line here represents the liquid plus crystal system viscosity. So we can see, so the take-home message for this diagram is we at least need something 58 volume% crystal to generate or higher crystal content to generate enough high viscosity compared with previously published physical model to account for the dome formation. And on top of this, I also think about degassing. And in this example, I run mineral 13 composition over there, which is I just involve 1 weight% initial bulk water in the system as the magma evolves. So somewhere 1100 degrees C, the magma bears 2 weight% water. And on top of this, I just doing depressurization to mimic a degassing in the volcanic conduit. So we can see the depressurization from, like say, 1 gigapascal to the surface pressure of Venus, which is 0.01 gigapascal. That can only increase the liquid viscosity by something 1 order of magnitude. That is still far away from the physical model of viscosity. So that means I just run follow-up surface equilibrium precision to accumulate more crystal. So we still at least need something 60 volume% of crystal to generate the high viscosity to account for the dome formation. And here's the conclusion. Fractional precision models generate more silica-rich conditions, especially at a lower pressure. Mineral 13 and mineral 14 combination have strong diverging liquid paths. The calculated purely liquid viscosity for both conditions are too low to account for dome formation. There's large uncertainties of initial bulk condition do not trigger large variation for the viscosity. We need at least more than 50 volume% is required to surpass the critical viscosity for dome formation from previously published physical model. So this result further underscores that the crystal content rather than the lava condition is crucial in determining the lava dome morphology or critical viscosity for dome formation. Thank you very much.